This week in class, we're talking about Ethernet LAN technology, local area networks. And so Ethernet operates at the data link layer, but it also operates at the physical layer. And Ethernet is part of the IEEE 802 specification. Ethernet is 802.3. IEEE 802 deals with LAN and local area network and MAN technologies that operate at layers 2 and layer 1. Data link layer and physical layer. So you have an Ethernet frame, but you also have an Ethernet NIC, the Ethernet network interface card, physically at the physical layer, which connects to an Ethernet straight through Ethernet cable, right, at the physical layer. So let's take a look at the sublayers of the data link layer, and then we'll eventually be able to get to how it relates to Ethernet. By the way, the IEEE 802 specification, this group first met in 1980 in February, so that's where you get the 802 from. That's kind of curious. So there's two sublayers in the data link layer, the LLC, the logical link control sublayer, 802.2, and the LLC is implemented in software, not hardware. It's the upper of the two sublayers in the data link layer. It provides services to the upper layers, layer 3. It provides flow control and multiplexing for the logical link, not for the physical link, but the logical link above it. So we're talking about the information that needs to go to the network layer that's in the ether type field, which essentially lets us know what protocol we're dealing with at the upper layers, what the encapsulated information in the frame has, where it's going on the upper layers. Also, our 802.1q VLAN tags. So your device is connected to a switch port and it gets part of a VLAN. Well, we need to know what VLAN tag that is because that's going to define what network it's going to be in at layer 3. So those VLANs help multiplex the communications to the network layer to the type of network it's going to be a part of based on the VLAN tag. All right, then at the lower sublayer, we have the MAC sublayer, the media access control sublayer, and this abstracts to the hardware NIC. The MAC sublayer does a lot. It controls how devices access the medium. So CSMA CD, or collision recovery, if we're dealing with Ethernet, it was designed to handle collisions on the wire in half duplex. CSMA CA, collision avoidance, if it's wireless Ethernet, we can't have collisions, we need to avoid collisions, we use wireless access points to help us with that. And then token ring, if it's not Ethernet, maybe it was another technology like token ring, which was a collision-free type of way of accessing the wire. You had to have the token to get on the wire. So that's not Ethernet. When we're talking about Ethernet, we're talking about the 802.3 specification, part of the 802 family, and it involved having MAC addresses that help identify hosts on an Ethernet network. It was designed as a shared network where everybody's on the network at the same time. Well, how do you identify those hosts? You have to have some form of addressing at layer 2, and that's the MAC address. So the media access control sublayer also deals with the layer 2 framing, encapsulating and decapsulating packets into frames and then back again. It's responsible also for the half duplex retransmission and back off functions. If there's been a collision and we need to retransmit, it deals with that. It can pend and check frame check sequence, or FCS, discard malformed frames, and enforce the interframe gaps in between frames. So it deals with error checking on the frames. It's also responsible, the media access control sublayer, for prepending, for transmitting, and removing, for receiving the preamble or start frame delimiter from the frame, letting you know that there's an Ethernet frame coming on the wire. So this is all done. This is at the hardware layer, that we're doing this, and also adding padding to the frame for the interframe gap. So that's pretty interesting, and that's all happening at the sublayers of the data link layer, the LLC and software, the MAC sublayer and hardware. So carrier sense multiple access with collision detection, designed for 802.3 Ethernet. What happens is your network interface card, your network adapter, is listening for a carrier signal on the wire. You send in an Ethernet network if no one else is sending. It was designed for shared media, meaning bus networks originally with coaxial cable. We had hubs in the early days, and if two devices send at the same time, you get collisions. Now you try not to do that because you're sensing on the wire to only send when there's no signal on the wire, but it happens where two devices are listening at the same time, there's no signal on the wire, they both send at the same time, and you get a collision. Another aspect to this is that we can identify devices' MAC addresses, and there's multiple access on this medium. So if you're going to have multiple access on the medium, each host or device that's on the medium needs an address. So MAC addresses provide the addressing to identify those devices on that shared medium. Resolving collisions. Collision detection, basically detecting a collision, sending a jam signal, and then running a back-off algorithm so that you can wait a little while before you can send again. That's the essential gist of it. If we break it down even further into steps, basically you're sensing on the wire, carrier sense. So a device with a frame to send listens until there's no carrier signal on the wire. Send, you begin sending the frame. You're listening, you're continuing to listen for collisions. Collision. If a collision occurs, the sending device sends a jam signal to notify all devices to stop sending, and then you wait before resending. Each sending device runs a back-off algorithm to set a random wait time before devices can begin to resend. And then after the wait timer expires, the process begins again. You can resend, and the process begins again where you're sensing, no one's sending, and then you can send. So essentially, this is the steps in CSMA-CD, carrier sense multiple access with collision detection. Now, what about these MAC addresses that you have in Ethernet? Every device, every NIC, every network interface card or network adapter has a MAC address. And a MAC address consists of 12 hexadecimal characters. The MAC address is also a 40-bit address. The reason it's a 48-bit address is that each hexadecimal character is the equivalent of 4 bits. So 12 characters, 4 bits each character, you have a 48-bit address. So this is what it looks like. So this is an example. I just made this number up, but this is 12 hexadecimal characters like a MAC address. The first 6 hex characters is the organizational unique identifier. This identifies the manufacturer of the NIC. So if you have the first 6 characters on your MAC address is E8B748, you have a Cisco NIC. And then the last 6 characters is the vendor assigned portion. So this means the first part means it's a Cisco NIC. The second part is what Cisco assigns to the NIC, and that's supposed to be unique. There should not be another Cisco Ethernet port with this number on it. MAC addresses can be colon separated, they can be dot separated, or they can be dash separated, and they can be all caps, but they can also be lowercase with the hexadecimal characters. A MAC address is a physical address. It's also known as a burned-in address at layer 2. MAC address is actually physically burned into the NIC, the network adapter. All right, now what about the Ethernet frame? So this is kind of a fun diagram that I took a while putting together, kind of nerded out on this. It's my Ethernet frame format. So this is what the Ethernet frame looks at. So at the beginning of the Ethernet frame, you have the preamble. The preamble is 7 bytes of 101010. It's the preamble before the frame. And then the start frame delimiter that shows that we're about to start an Ethernet frame goes 1010 and then 1011, and that's the start of the frame. Now this is 8 bytes, 7 for the preamble, 1 byte for the start frame delimiter. This is actually not part of the Ethernet frame. This is before the Ethernet frame. The Ethernet frame is the destination MAC address, 6 bytes. In the frame it says where the MAC address that you're trying to send to. And then the source MAC address, the MAC address of the device, the NIC that it's coming from. That's 6 bytes. Then you have the ether type field. Depending on your type of Ethernet frame, it could also be called the length field. The length field would have the length of the Ethernet frame. The ether type field has a 4 hex characters that are 4 bytes. 2 bytes that indicate whether it's an IPv4, packet in the payload, or an ARP packet in the payload, or IPv6 in the payload, or so on and so forth. So there's different types of ether types saying what's in the payload. Now, what about the payload? The payload is typically 46 to 1500 bytes. Well, this is what it is. It's 46 to 1500 bytes, or 42 to 1500 bytes if it's got an 802.1q VLAN tag. At the end of the Ethernet frame is the CRC, the cyclic redundancy check, which is a frame check sequence of 4 bytes. And this is used for making sure that there's no errors in the frame. And then between frames, you have the inner packet gap. So now if we look over here, we can see that the Ethernet frame size is 64 bytes to 1522 bytes. 64 bytes minimum size, 1522 bytes maximum size. So where do we get that? Well, we take the payload size and then the header and trailer size. This is the header over here. This is the trailer. So 6, 12, 14, and then the trailer, another 4. That's 18 bytes. 18 plus 46 is 64. 1500 plus 18 is 1518. The extra 4 bytes to reach 1522 is the 4 bytes that gets added with the TPID field of 2 bytes and the tag control information field of another 2 bytes. Now let's take a look at this information. So we've already said the frame size, 64 minimum, 1522 bytes maximum. The TPID field, tag protocol identifier field, is set to 8100 if you have an 802.1q tagged frame. Now this extra 4 bytes gets inserted into the frame between the source MAC address and the ether type field. And the TPID will line up on the left-hand side where the ether type field was. Now the ether type field indicates what protocol we have in the payload and what type of protocol is going to go to the upper layer. So the ether type field is 4 characters, 0800 if we're dealing with an IPv4 packet at the upper layer, 0806 if this is an ARP packet, 86DD if it's IPv6. Now, if it's an 802.1q VLAN tag has been added in and there's an extra 4 bytes, it gets put in right here, and the leftmost part will be 8100, which will signify 802.1q tag, and that will line up in the same place where you would read the ether type field. Then you have these other fields that get inserted into the Ethernet frame also. The priority code point, PCP, is 802.1p. This signifies class of service or quality of service if it needs priority handling. The discard eligibility indicator will indicate congestion upstream. So the DEI gets a 1-bit, can get set to indicate congestion. And then you have the VLAN ID, which is 12 bits long, which allows VLAN tags up to 4094 VLANs. 0x000 and FFF are reserved. Then a little bit more about the cyclic redundancy check or frame check sequence. In the past, I've always described it as a hash to make sure that the frame is error-free. At the receiving end, you could recalculate the hash to make sure it's error-free, but that's not true. What it actually is, the cyclic redundancy check, is a form of parity bit check where they have n bits plus 1 and they do an exclusive OR operation on the bits, and if bits have changed, if there's less bits or added bits or fewer bits, then you're not going to get a matchup on your bit check, and that'll mean that there's been an error in the frame. It's not the same amount that was sent that was received. So there's been some change in the frame. Usually maybe bits were missing because of some type of collision or something like that, and so it's a form of error checking. But it's like a parity bit check. It's not really like a hash. So that's the cyclic redundancy check frame check sequence that is at the end in the trailer of the Ethernet frame. So anyway, that's pretty cool. So the ether type field protocol numbers. Ether type field protocol numbers indicates which protocol is encapsulated in the Ethernet frame, essentially showing you the different types of protocols that can be in the payload. So it could be an IPv4 packet if it's 800 here. If it's 806, it's ARP. It could be reverse ARP. It could be, there could have a VLAN tag in it. If there's 8100, then you know there's a VLAN tag in there. 86DD is IPv6. You've got link aggregation control protocol, MPLS, PPPoE frames. It could be an EAP over LAN, 802.1x for EAP over LAN. It could be SCSI over Ethernet. I mean, just all types of different ether type fields. I was kind of geeking out on that.